4.2 explainer. If a car stops suddenly, you feel thrown forward. We like to imagine what happens to the passenger as a car stops. Imagine yourself sitting on a bench inside the car. This bench has no friction and there's nothing to hold on to. Concepts we are going to go over are inertial frames, free body diagrams, Newton's laws, how forces interact with each other, and cause motion. So we draw a picture and identify all the forces acting on you as the car travels at a perfectly steady speed on level ground. And we're going to draw a free body diagram. There's a couple parts to this problem. So we'll see. We go up to part F. So I drew a picture here of the car, and I think a lot of people would assume we want to find what's happening to the car. So you're going to do in the reference frame of the car, but the question is actually asking the reference frame of you. So in reference to you and not the car. So people would think, oh, we're changing speed. There's going to be like frictional force, all this, normal force, gravity. But really, there's just going to be two forces, and our net force is going to equal to 0, and that will be our normal force and our F of G, or our weight. So our G is what's going down. You sit, your weight, your gravity times your mass is on it, and then the chair is exerting a force back against you. That's our normal force. So it's right here, free body diagram. Our F of N, our normal force, is equal to our F of G. They're proportionally equal to each other. That's why you don't fall through, or when you sit down on a chair, you don't spring up. So our net force is going to be equal to 0. Repeat A and B, but with the car slowing down. So actually, with the car slowing down, this is still in reference to you, it's going to be unchanged. So our free body diagrams are actually going to be the same as part A and B for part C. The car, you mind the same, so the car slowing down. So our forces on the car are changing, but our forces on you are not changing. Describe what happens to you as the car slows down. There's a force slowing the car down, but there's no force on you. So the diagrams are unchanged. Use Newton's laws to explain why you seem to be pushed forward as the car stops. So Newton's laws state that an object in motion will stay in motion, or an object at rest will stay at rest unless a net force acts on it. This is Newton's first law. And remember, we have our net force is equal to 0. So if there's no friction, if there's no force acting, pushing us forward or against us, we're just going to continue at a constant velocity forward. So this guy's just going to move forward, and obviously that will change if, let's say, he was wearing a seatbelt, or there's like friction on the seat, or he hits the window, or he holds on while he's slowing down, right? But we're assuming none of that happens, so he's just going to keep going in a straight line forever and ever and ever, according to Newton's first law. Part F, suppose the bench is not slippery as the car slows down. You stay on the bench and don't slide off. What force is responsible for deceleration, and what direction does the force point? Include a free body diagram. So now we'd assume, which most benches, right, it's a little rough, there will be friction. So if you're staying on the bench as you slow down, then you're gonna have a net force. It's not necessarily gonna equal 0, and your velocity is now decreasing, which is gonna be caused by static friction. If it would be kinetic friction, that means you'd be moving, but you're staying on the bench. So the static, if the force on the car was decelerating faster and you're still staying on the bench, then the static friction you see here is going to be greater than the static friction if it was decelerating a little slower. But you're not moving, so you're going to have a static friction. And where people might mess up is they assume that we want to find the force on the car, but it's in reference to you, and assume that forces change when slowing down. But remember, this is still in reference to the person and not the car, so that wouldn't change anything. And this is an inertial frame, so like with the static, our static's not changing if it's decelerating faster or slower, because in inertial frame there is an acceleration in inertial frame, so there's not a change. It's just at that moment. So we're looking for something at that moment and not over time.